Today's lesson 2, and we're looking at exponential growth and decay in the real world. So a couple of the biggest things we use this for in the real world are investments. So if you're investing money in a bank account and you're earning interest, or if you're paying off something that has accumulated interest, and also population. So population is something that can increase or decrease, but it can increase and decrease at an exponential rate. So those are the two biggest real world situations that we are going to work on today. The first formula we're going to look at is going to be the periodic compound interest formula. And the periodic compound interest formula is when you are specifically dealing with interest that is either compounded annually, semi-annually, quarterly, monthly, weekly, or daily. And for this, we fill in this equation. We have A, which is equal to the account balance. We have this set equal to the principal or the amount invested. So it's whatever you start with. I should put starting point as an extra note. The equation goes 1 plus R. R is the rate as a decimal. So for example, if you had a 2% interest rate, meaning you had a bank account that was earning 2% interest, you would need to write this in the formula as 0.02. That's the decimal. So you move the decimal place over 2 places to get the form we're looking for. All right, so the rate is going to be divided by the number of times compounding per year. And the number of times compounding per year are these values that we talked about. If it's annually, your end value is 1. Semi-annually, the end value is 2. Quarterly, end value is 4. Monthly, end value is 12. Weekly, your end value is 52. And daily, your end value is 365. Use these. Don't make up new values. Use the ones that I gave you. All right, so after we fill in 1 plus the rate over the number of times compounding, we have an exponent, which is the number of times compounding again, multiplied by the time in years. It's important to know that the time is in years. If by chance something gives you the time in months, you need to calculate that out to the decimal of a year. Example 1 says that Christy invests $300 in an account with a 6% interest rate. Making no other deposits or withdrawals, what will Christy's account balance be after 20 years if she does not make any other deposits or withdrawals? So we're looking at two separate problems. We're looking at compounded semi-annually and compounded daily. In either case, we're going to be using the formula we went over above, which is A equals the principal amount multiplied by 1 plus the rate over the number of times compounded, raised to the power of the number of times compounded, times time. The principal amount is what we're starting with. For compounded semi-annually, we're starting with $300. The rate is the percent interest rate that the account is using. Here we're using a 6% interest rate. When you write percentage as a decimal, that's what you need to use for your function, you would rewrite 6% as 0.06. Next, we have the number of times compounded. This tells you that this function is compounded semi-annually for part A. So our end value is compounded semi-annually or twice. If you don't know that, it's in this chart we went over above. And the last piece of information is the time. So how long are you leaving the money in the account? In this example, it says that Christy is leaving the money in the account for 20 years without touching the money or touching the funds. So we have all of these values that we need to substitute into the formula that we just went over for compounded periodically. When I substitute these values into the function, I have 300 multiplied by 1 plus the rate of 0.06 divided by 2 raised to the power of 2 times 20. And when I type this into the calculator, I'm going to use Desmos Scientific. So I'm going to switch my screen to Desmos Scientific. And actually, before I do that, I'm just going to indicate you do have to put parentheses around your fraction. So you end up with two sets of parentheses within this expression or within this part. Make sure you include those parentheses. They're absolutely important in order for your calculator to read the correct order of operations. So right here is where I'm entering my second set of parentheses. So you should all practice typing this in, making sure you get the same answer as me. Over here on the right side of the calculator screen, you can see that my output is $978.61. When you're working with money, you should just get into a good habit of rounding to the nearest hundredth. That is what money would typically be rounded to, 2 decimal places for change. All right, so answering the question for compounded semi-annually, you would say that after 20 years, you would have $978. So she started with 300, that means she earned $678.68 over the course of 20 years. Next, let's take a look at compounded daily. So this would be the second part. We're going to use the same equation to start with. Our values are going to change slightly, and when I say slightly, it's really only the end value that's changing. Our principal amount is still 300. The rate is still 6% or 0.06. This time we are compounding daily. So in the chart above for compounded daily, you're going to use an end value of 365. And for time, we are still looking at 20 years. So when I substitute this into the equation, I have 300 multiplied by 1 plus 0.06 divided by 365 raised to the power of 365 times 20. And switch back to Desmos, we're going to type this in. It's actually a very similar function, so I'm just going to use what I already have, and I'm going to change my denominator of the fraction to 365. And I'm going to change part of my exponent to 365. That gives me an output of $995.94. So over the course of 20 years with Part B, Christy would earn an additional $695.94. Continuously compounded interest. So continuously compounded interest has a slightly different formula. It does use some of the same letters, but we have something a little bit different that we're going to use, and it's called the number E. So we'll talk about that in a second. But we have our account balance, which is going to be our solution. And in the formula, we still have our principal amount, so the starting amount. This right here, hold on. This right here is a button in your calculator. All right, so that's not a value that we're substituting anything in for. That is literally a button in your calculator. This is going to be raised to the power of your rate multiplied by the time in years. Again, if you are given the time in months, you need to convert that to a decimal in years. So I'll show you where the number e is in the calculator once we go over a couple of these problems. For the first set, it says suppose you won a contest at the start of ninth grade that deposited $3,000 in an account that pays 5% annual interest, compounded continuously. You start college 4 years later and you spend 4 years in college. About how much will be in the account after 4 years of college? So you have to be careful because these word problems are all going to be mixed up. So you need to pay attention to the language. The word problems are going to tell you what type of formula to use. Right here it says compounded continuously. That tells you that you are using the compounded continuously formula. So that tells me that I'm using the equation A is equal to the principal amount multiplied by E raised to the power of rate times time. My principal amount is the starting amount, which in this case is 3,000. E is going to be in our calculator. Next, we need to look at the rate. And the rate tells us it's 5% annual interest. That would be as a decimal 0.05. And lastly, we're looking at time. This says we want to know after 4 years of college how much will be in the account. Well, we earned it at the start of ninth grade. 4 years later, and then 4 years in college. That makes a total of 8. Ninth grade till you graduate is 4 years, 4 more years in college, that's 8. When we substitute these values into our formula, we have 3,000 multiplied by E raised to the power of 0.05 times our value of time, which is 8. And now I'm going to switch and show you in Desmos Scientific Calculator how to type in the number E. Okay, in Desmos Scientific we have 3,000 multiplied by E, so I'm going to select function, which is directly below my cursor, slid over to the right. Hit function, and now if I'm looking at the right-hand side keys, I'm going to go 3 rows over. I see that I have what looks like an E raised to the power of X. I select that, which drops in my number E, and now gives me the opportunity to type an exponent, of which I type 0.05 multiplied by 8. And you can see I get $4,475.47. So starting off with $3,000 at an account that earns 5% interest, 8 years later, this account earns an additional $1,475.47. Okay, I'm going to do the on your own section by myself. You guys can watch as I do that. And we're going to stop right here today, saving the last part, which is population, for tomorrow's video. The next two formulas that we're looking at are for population. Population can be increasing or decreasing. So to start off with, let's look at exponential growth or decay. This is actually the same formula as the first one we went over on the first page of notes, except for when you're looking at exponential growth or decay, you're looking at an annual rate. Therefore, the n value that we learned about on the first page is always going to be 1. And if it's always 1, then we really don't need to write it because a fraction over 1 is just the numerator. So we can simplify it to this expression here. So just to clarify what I mean by that, if we were to use the equation from the first page, we would have r over n raised to the power of n times t. But if n is just 1, it's not necessary to write that. Everything else is the same. I would like to highlight the fact that the principal amount in a population would also be the starting population. So in a population problem, it's the starting population. And one thing about the rate is when you're talking about population, it can increase or decrease. So the rate could be a negative number. We could also see continuous exponential growth or decay formulas, problems. So this is the same as the continuous function we went over above. If you have the principal amount or the amount invested in a population type problem, the p-value would be your starting population. So for the first one, we're looking at the fact that Mexico has a population of approximately 110 million. That would be 110,000,000,000. If Mexico's population continues to grow at a rate of 1.42%, predict the population of Mexico in 10 years. We're looking to do this both annually and continuously. The annual formula is the principal amount multiplied by 1 plus the rate raised to the power of time. I know that the principal amount, or the starting population, is 110 million. I know that my rate is 1.42%, which converts to 0.0142. And I know that the time I'm looking at is 10 years. When I substitute these values into the equation, I have A equals 110 million multiplied by 1 plus 0.0142 raised to the power of 10. And if I was to type this into my calculator, I would have a population rounded to the nearest whole number of 126,656,869. And you round to the nearest whole number because you're working with population of people in this case, so obviously people would be whole numbers for it to make sense. Next, we're looking at compounded continuously. Compounded continuously uses the equation of A equals P multiplied by E raised to the power of RT. The principal amount is 110 million. The interest rate is still 1.42% or 0.0142, and the time is still 10 years. But we're substituting this into a different formula. So we have 110 million multiplied by E raised to the power of 0.0142 times 10. And if I type that into my calculator, I have a very similar answer. This one is 126,783,431. So not far off from the first example or from part A. You are going to end up with similar answers. The interest rate is obviously the same, the starting amount is the same, the time is the same. The only thing that is slightly different is the formula that you're using. So is the population compounded annually or is it continuously? Those are two different formulas. All right, and for the on your own section, I'm just going to put my answer on the screen here. I think we've gone through quite a few of these examples. There's one thing I just want to point out on the on your own section. So for the town population, it's declining at a rate of 6%. So when you check out my answer, you're going to notice that declining means that it is subtracting. So the rate is actually decreasing. Okay, for the last example, we are actually working backwards on these. So we have the data, but we're going to have to find the rate in order to answer the question. So this one says the table shows the number of reported cases of chickenpox in the United States in 1980 and in 2005. Use the given information and the exponential growth formulas to answer part one, which says if the number of reported cases of chickenpox is decreasing at an exponential rate, identify the rate of decline and write an exponential equation to model the situation. All right, so we're going to be using the equation A is equal to the population starting point multiplied by 1 plus r raised to the power of t. But we need to figure out what we have for data. So right here, we know that this is our initial amount because it's in 1980, that's the starting year. So this here will be considered the initial amount. If it's the initial amount, it's the value of P. Knowing that we have our data compared between 1980 and 2005, we know that this number 32.2, that's in thousands, is going to be our ending amount, which is the value of A. We've actually never had the value of A before. We're usually solving for A, so that's something different that we're looking at. We also know that the time it takes from the initial amount to get to the ending amount, so the time it takes from the population of cases to start to the time that it ends, is found right here in the table. And this is found by subtracting 2005 minus 1980. And the solution here would be 25 years. So the time is 25. All right, writing down everything we know. We have our initial amount. We have our ending amount. We have the total. Our answer is 32.2. We have our initial amount, or the starting population, which is 190.2. We are missing our rate, so we need to find the rate. And lastly, we know the time is 25 years, and it's 25 years from the start of 1980 to the end of 2005. So if we take these values and we substitute them into the equation of P multiplied by 1 plus the rate raised to the power of t, we would substitute this in as 32.2 is equal to 190.2. It's 190.9 actually. Plus 1 plus the rate, which we don't know. I'm going to use the variable r for that, all raised to the power of time, which is 25 years. All right, we're looking to solve for r right here. And if we're looking to solve for r, that means we need to isolate that value. So I'm going to divide both sides by 190.9. Which leaves me with a decimal of 0.168 0.67, and this is equal to 1 plus r raised to the power of 25. Well, if you remember from solving earlier, if you have an exponent, you can, for lack of better terms, undo that exponent by taking the radical. We are looking at 25, so if we take the 25th root of each side, we are going to, again, just for lack of a better term, undo that radical on the right side. The square root of 0.6867, not the square root, the 25th root of 0.1686747 is 0.93128, and this is equal to 1 plus r. We're solving for r, so subtract 1 from both sides, giving you r equals negative, rounded to the nearest thousandth, we'll do 0.069, which is actually equal to negative 6.9%. That's your r value. So the directions say to identify the rate of decline, which we just did. And it also says to write an exponential equation. So we're going to write the equation as a equals 190.9 multiplied by 1 minus 6.9, and this would be raised to the power of t. Okay, that way we can substitute in any year. We don't specifically need either year 0 or year 25. We could substitute in any year and figure out what the population of the chickenpox is. We're going to cross off number 2 because we don't all have graphing calculators this year. And we're going to move down, and I'm going to go over part A in the on your own section. We can also cross off part B here. We don't have a graphing calculator. Are using the data in the table and we're assuming that the population of the Miami-Dade County is growing exponentially. We have a couple things. We know that in year 1990, the population is 1.94 million, and we know in 2000, the population is 2.25 million. So just starting off, I'm looking at this, and the difference between the years is 10. I know that the population in 1990 is your initial amount, your p-value, and I know that population in 2000 is your ending amount, or the a value. So I'm going to substitute in everything I know into the equation a equals p multiplied by 1 plus r raised to the power of t. I can substitute in the fact that we have our ending amount at 2.25. This is equal to 1.94 multiplied by the value of 1 plus the rate that we're looking for, raised to the power of 10. Divide both sides by 1.94. We have 1.15979 is equal to 1 plus r raised to the power of 10. We can take the 10th root of both sides, and in this case, the 10th root of 1.15 is 1.0149. This is equal to 1 plus r. Subtract 1 from both sides. Your r value is equal to 0.015. This means our R value or our rate is 1.5%. It's increasing. So if the directions tell us to write a function, I could write this function as a equals 1.94 multiplied by 1 plus 1.5 raised to the power of t. So we could substitute any time and we could find out the population of the Miami-Dade County. Remember, you're only substituting values into your final answer that would allow you to solve for any time. So you definitely don't want to include your answer because obviously that wouldn't allow you to solve for any time. And you would want to leave t as a variable as well. Leaving t as a variable allows you to substitute in any year.